Bonded contacts, we give mostly bonded contacts near the bending joints, or maybe welding joints, or maybe at brazing joints. These are the brazing joints, and the welding joint we give bonded contacts. And some areas we just give it only contacts which we need only, no separation contacts. For example, this is a rubber grommet. It should not be, it is not touch, just wait, it should not touch with the bolt of the component. So only, it should not be separated from the bolt of the component. It should be only, as we put the rubber grommet on the upper side, it should not be removed from that. So we give no separation contacts. So these contacts play a major role. If we give any contacts, we didn't give any contacts carefully, it can be a there can be different dynamics, and it can cause a different results. So which are not be which will not be equivalent to the exact testing data. So we have to take care of the contacts, and after that we have to conduct the meshing. We have to put meshing on the pipe, separate meshing for the piping. Meshing of piping should be a less than 1 mm during NVH analysis, during model analysis, because it is a critical part on which we have to work. So how much discretize we should do this piping, it give us a much better result. After that, we just give a boundary condition that fixed supports on the bottom side. We have done analysis settings. We have to, for example, how many number of modes we need in this. For example, I have mentioned only 6 number of modes, because if you say, we can say why 6 number of modes, because we have 6 degree of freedom of any element. But however, this is not a method. We have to extract the more than 36, or maybe more modes in that, because how we have to know that how many modes we needed. This is for reference only. That's why I've just extracted 6 modes. But how many modes we need, this we can extract it from the solutions. So these are the effective mass criteria. So if the value of this effective mass ratio goes up to 95%, so then up to till we have to extract the modes. Up to 6 modes, only 84%. So these are not sufficient. So what are the effective mass that which what effective mass means, which area or which mass is affecting a lot in a layman term, which area or which mass of that component is affecting a lot. So we have to extract that number of modes. For example, in 6 mode only 84, maybe we have to extract a 24 mode, or maybe 12 mode. We will put value here, 12 modes. We can 12 modes here, and then we can extract the number of modes. And then if we observe the value here up to 95%, till then we have to extract the modes. So 6 modes we have extracted. So these are the first. This is the first mode. If you will see, play it. So as you see, it is first mode is showing in on suction and discharge by both, and then we go ahead with the second mode. Again, it is showing on the same area. Third mode, if you will see, it is showing only in discharge. So it means at 23 hertz, its natural frequency 23 hertz near this area. So we have to, as you see, we have put some weight in the. This is a point mass we have put on a piping. It's a 50 gram of point mass to avoid to avoid resonance, to reduce the natural frequency of this pipe. Before this, it can be more, it can be higher side, but by adding a weight up to 50 gram, it get reduced. In physical condition, we put rubber grommets on the piping to gain this to gain this frequency, to get this frequency. And again, the mode is coming in compressor side, and fifth mode is coming in a accumulator side. So this is how we extract the natural frequency. And in the end, as I already told you, we just put and we don't have a value to extract the harmonic analysis, harmonic values, how much the component will be vibrate. We have to know that how much component will vibrate during a real compressor condition. But we cannot model the real compressor condition in here because we don't have force values. In some cases, we use in this grommet area we put load cells and we extract the force value. In simulation we use these force values to extract the exact vibration. So but in that case, if we don't have that force value, we use 1 Newton of force in any direction, x or y, not in a vertical direction, vertical direction, in x and y direction, to extract an exact impact on pipe. So in this we can in this we can extract which area. For example, I have to extract the vibration values near on a discharge pipe. So we can select this pipe and we can extract the frequency response, and we should get the data. We can get the value near the significant frequency or how much it can be go. This is a very higher side. It is not. It is in a. We can extract this value on the in these areas. What we can extract the frequencies, which frequency is impacted a lot. For example, in this area, in piping, if you observe 26 or 11 hertz, it is in pipe 11 hertz and 27 hertz. So these are the impacted frequencies. We can check here how much amplitude it can go. But uh, in reality, we need exact force value, which we can extract from a load cell. So this is how we extract the value, and we can evaluate that which area is impacted a lot, and we can avoid the resonance, and we can avoid the vibration of the components by adding. We do iteration by adding, as you see in the as I already shown you that we put weight in like this, and we avoid the failure of the piping. When we can reduce the length, and we can do iteration again and again. So which is very difficult in physical testing, we can do it in a simulation. So this is all. So any question from anyone?
Okay, any query uh, from participant side? Okay, then we can continue, Mr. Sunil. We can continue.
So this is one of the simulation we have done, and this is one more simulation I can show you. This is a drop test of a chest freezer. So this is how if we'll tell you. Modeling part is not here, we can show, but this is a big part, and how it is getting fall. We are doing an edge drop simulation here. So this is a displacement value, and we can extract the stress value as well. On the various component part wise, we can extract the stress value, and how it is falling, which area is impacted a lot. So we can extract all these values. So this is a full assembly. We have just dropped it from 300 height. It is a corner drop. If you will be able to see how it is falling, which area is impacted, and we can check it. Okay, this is all from my side. Any questions?
Hello, any query? Participants, any query? So, hello, Mr. Sunil. Is it
Yes.
completed?
Yes. This is all we have done.
Okay. So, can you explain a little bit that the all the that parameters actually the options available in during the structural analysis means the interface no? Software interface.
Software interface, if you want to see this.
Just a little bit that where we can put the and the different values and how. Okay, just for the knowledge means the basic for the basic idea.
Okay. So this is ANSYS interface, and what you want to see. So this is the ANSYS we just started from here. If build ANSYS Workbench 2023 we are using currently.
Okay.
We can open it from here. After clicking, this window will be appeared, and this is what we do model analysis. We can click it here, and this model analysis pop-up will be occurred, and it can be. So from here we can extract, we can import the geometry, whatever the geometry, any geometry by bending, maybe we can show it to them. But I think just wait. It's okay. जो discovery. डबल क्लिक हो गया इसमें. ओके ज्योमेट्री में बना देते हैं. ज्योमेट्री 2 मिनट लगेंगे. एक बाइक बना के इसको. ये घंटा लग जाएगा. उसमें इशू आएगा, फिर से वो ज्योमेट्री वही खुलेगा उसमें.
राइट क्लिक करके वो स्पेसिफिक.
So this is what we do. We are going to make a geometry in space claim. This is space claim is a new tool given by ANSYS for geometry cleanup or making any CAD in this. So for geometry cleanup, and what geometry cleanup means, what if we want to remove any extra features which are not required during simulation. So we just use this tool for geometry cleanup and CAD making. This is space claim for geometry cleanup. It is similar to the CAD tool like SolidWorks and all, but little advanced for geometry cleanup and meshing and all. we can do meshing in this also, but it is not at a advanced state till now. But so for example, we are taking a piping. And we have to assign a thickness of up to 1 mm. So we got us, for example, we got a 3D like this from our design team, and just after that we have to repair the 3D, and we have to we can bring it to, so that we can able to bring it to easily. We can mesh, or we can model this to for meshing. So for example, we can get a 3D like this. We extract the mid surface of this component, and we however, we can import directly some 3D from here, directly import 3D in this, but at present we don't have the 3D, so we just, now we can go and we just edit for modeling.
So this till now we have created a pipe, and for structure simulation we deal with surface body. So we have extracted mid surface from that pipe, and after that we have saved that geometry file
Yes.
to a specific location, and now we are opening this model
Model.
software. Once it get open, we will import the geometry which we have created just now. Already put it. Yeah, since the software is launched in Workbench, so automatically it will import the geometry from the space claim. Slow down.
I think remote का भी जरूर
Nice.
है. License है. So this is the mid surface we extracted. So you will see thickness we have taken already 1 mm. So it is already imported here. Mid surface we have taken, we can easily mesh, and we can also change the thickness if we want to reduce the thickness to 0.8 mm. So it can be 0.8 mm also. So here we can extract, we can change material property. We can add material also if we want to add the materials. We have a material library here and engineering data. Here we can go to engineering data source. This is a dedicated library from Ansys. So, for example, we have to add copper piping. So we add copper piping in that. Now we should go directly here. We can refresh the materials. Copper material will be added. So in mid surface now we can, as you see, the first property we had given was the material thickness. Now we have to give the material property, what kind of, which material we are using. So we can change it from here, the copper alloy. After that, there are meshing option. This is the coordinate system. It is this coordinate system is given. It is already pop up here. If we want to change it to somewhere else for some another boundary condition, we can change it somewhere else also. But the next one is the meshing part. Here there are many options which at present is a we can use face meshing for this. You can change the this size from here also. As I said, my piping is a smaller in size, so lower diameter, lower size of mesh size is okay. Will be better for. Let's see. This is a quad mesh. It is formed all over the pipe. Now this is a model analysis we to extract the natural frequency of the piping. So for that we have to give a boundary condition. For example, I'm fixing this edge of the pipe, and as I already know, number of modes I only have, if I give 12, so we can directly run it from here. Boundary condition one of the boundary condition is given. It is fixed from here, and we can just run the analysis. This is a single part. Otherwise, we have to give contacts also. One part is missing. The contact is missing. A single part we just give boundary condition. We can directly run the model. So these are the natural frequencies you can see are extracted. So these are the modes. If you see, first mode is like that. For example, it means if we fix at one end, so this is the eigen value of this pipe for natural frequency. It gives a 465 hertz of natural frequency because it is very low. I think is lower in length, so that's why it's giving this much of. So second mode should be of a different type. Third mode is in the. This is the third mode shift. It will get bent at that point at 2717 hertz. It is too high, but if this pipe is undergoes this 2717 of um, working frequency undergoes the 2700 of working frequency, it should get damaged. It get caught in a resonance. So we have to avoid this. We need to change either the shape or we can add the weight on that to reduce the natural frequency. So this is the way we do the simulation, and these are the another modes in this, the piping. Similarly, if we and give one more boundary condition, we can expect another modes and all. So this is how it works in as we see in earlier piping simulation also, and here also. একটা बना दिखा दो। बंद करो। Any question from anyone?
Hello, participants. Any query?
At present, are you conducting any kind of simulation or doing any simulation in your or in your college, anyone structural simulation?
Yeah, that's correct. Is there anyone who is doing a structural analysis in any types of research work or any experiment from the participants? Anyone who is doing a structural analysis? Okay, so okay, how many of you are doing CFD analysis, fluid dynamics analysis, in any research work or in any project type? So no one is here who is doing the simulations work.
Anyways, this is the last I'm just presenting you. This is a washing machine tub of fully load, top load, fully automatic washing machine. Outer tub is this. So we have done the natural frequency analysis of this component. For example, we have just give boundary conditions on the mounting locations. These are the mounting locations. If you see these are the four mounting locations are there. We just fix it here. Fix this here on four sides, and we have extracted the modes from this. So this is the first mode. For example, this is the first mode, and 51 hertz means if our machine will run at 3000 rpm, it will get resonance. It can be a higher vibration and all. So it to avoid this, we have to change the structure. So this is what we can extract from the model analysis. So similarly, as I already told you, another modes are also there which are impacting 52 hertz. So if any working frequency, for example, the inner tub inside this tub, there is a one more tub is there. If it should work, it should run at 3000 rpm. Means it should be near to 51 hertz or 52 hertz. So it can cause a severe vibration and can cause a severe noise also, vibroacoustic noise also. So this is how simulation is helpful. This is all from my side. Any question again?
Okay, participants, any question? Please, I request if you have any query, then you can ask. Am I audible to the participants? Okay, then I think now it's concluded, right, Mr. Sunil?
Yes, yes.
Oh, okay, then thank you for these nice structural presentations. Actually, I have also learned many new things for the structural analysis. So, Dr. Satyans, can we conclude with today's session? Dr. Satyans, I'm audible.
Yes, sir. You are
Hello.
audible.
Okay, so we can conclude, I think, this today's session.
Okay, thank you.
Yeah.
Okay, then thank you, Mr. Sunil. Thank you for the nice presentation, and thank you to audience. We will resume our this short-term course again tomorrow from 10 a.m. Thank you all.
Yeah. So the Professor Anil will be talking about optimization of solar thermal systems. So which is of utmost importance to everyone, and nowadays one of the latest problem where everyone is supposed to deal with. So I hope it will be great learning to all the participants. So I hope you all will join on time tomorrow as well. Thank you so much.
Thank you.
And in the second session, which will be our workshop session, in the workshop session, we will discuss, we will go